Alright, so we are going to look at a problem that deals with finding the potential around two thick conducting hollow metal shells, as shown here, that has a point charge plus Q right at the center of the inner shell. The inner shell is neutral and the outer shell has overall charge plus Q. And they're both metal, so that means they're both conductors. Okay, so the thickness cannot be ignored. These portions are part of the metal themselves. All right, so this is also part of the metal, and we want to calculate the potential everywhere in space around this setup. Okay, and the radii are given. A is the inner radius of the inner shell, B is the outer radius of the inner shell, the outer thickness, C is the inner radius of the inner shell, outer shell, and D is the outer radius of the outer shell. Alright, so I want to just go over the basic recipe of finding the potential. So we usually what we do is we apply Gauss's law. Once you apply Gauss's law, it becomes very easy. You just do the integral to calculate what your potential is. So the recipe to calculating the potential is, first you find your electric field using Gauss's law. So E dot dA is equal to the charge enclosed by the Gaussian that you're selecting over epsilon 0. Once you get the electric field from here, the second thing that you do is apply your potential equation. So the potential is calculated by doing this integral, E dot dl. If you're wanting to find the potential from going from A to B, whatever A and B are, you just plug in the limits A to B. Alright, so this is the basic recipe that you can use to calculate the electric potential around something with symmetry. Alright, now we have done so many times the applications of Gauss's law. I don't want to go over this. I don't want want to find the electric field for you anymore. You should do that yourself. But I want to show you an easier way to calculate potential without doing integral. So without doing any integrals, integration, I want you to be able to find potential. Find electric potential. Alright, so that is a good thing for many of you. You don't like integrals, then let's go begin. So we start off with our common findings from previous discussions, from previous classes and previous lectures. We found that the potential expression for a sphere has two forms. One is inside a sphere and one is outside a sphere. So the potential inside is kq over capital R. So that means the R is the fixed radius of whatever sphere you're considering. So inside there is no change in potential from the surface. Sphere is an equipotential, and outside the potential goes as 1 over R. Alright, so we know that from previous lectures and many exercises that we have done. Alright, and K in both cases is just 1 over 4 pi epsilon 0. Alright, now let's find out the easy way. To apply the easy way, what then I want you to do is first be able to find the charge enclosed around any region. So we temporarily employ Gauss's law. So consider the inner shell, alright, and consider this inner shell, and we want to say find the charge enclosed, let's say inside the metal conductor, inside the metal shell. So we consider this kind of Gaussian. So we are looking to find the charge enclosed by this Gaussian. Alright, so what is the charge enclosed by this Gaussian? By definition, we know that this is part of the metal itself, so inside the electric field must be 0. So in this region the electric field must be 0. It's inside conductor. So then what is the enclosed charge? Well, we clearly see that this Gaussian is enclosing this positive point charge, but because electric field must be zero, then it and charge must always be conserved, then it definitely means that any electrons, any and all electrons, most of the electrons from this in this metal that are free will run towards Q and be as close to Q as possible, meaning that you will overall get a negative Q building up on the inner side of the inner wall, inner shell. All right, so then the charge enclosed is still 0, but Q inner is minus Q. All right, so that is what we have for this part of the shell. All right, so in a region which is less than A, which has radius less than or equal to A, then we have this charge. What about the next region? Well, we want to see now outside. So we draw a Gaussian that is outside, encircling the whole shell. So again, we see that this Gaussian is now enclosing plus Q, right? But remember, we said that the inner shell, this inner shell overall, this part is neutral. So if the inner shell is neutral, that means this whole thing, this whole shell, this thing is neutral, meaning it has no overall charge. If it doesn't have overall charge, but we just found out that the inner wall is negative Q, then that automatically means the outer wall must be positive Q. All right, so therefore this Gaussian enclosing a net charge of plus Q at the center, minus Q in the inner wall, and plus Q on the outer wall. So these go away, so the charge enclosed is still plus Q, so you will have definitely an electric field in that region, and that makes sense because it is just outside of a conductor in this hollow region of the outer conductor. All right, now let's look at the third region. So apologies for the writing in between. All right, now let me erase that for clarification. All right, so I think that should be fine. All right, now we want to find the electric field in the region that is inside the outer shell. So let's draw our Gaussian, and then let's see what the charge enclosed is. We don't want to find the electric field, sorry, I want to find the charge enclosed. So what is the charge enclosed? This Gaussian clearly sees this minus, this plus Q, but we have determined that the minus, that the inner wall is negative Q, the outer wall of the inner shell is positive Q. Then again, remember, this is part of the conductor itself. This region is inside the conductor. So here again, the electric field must be 0. This is inside conductor. If the electric field must be 0, then what is the charge enclosed? Then Q enclosed must be 0, which means that your outer wall, sorry, the inner wall of the outer shell must have some charge to balance everything out. So you have plus Q at the center, minus Q in the inner wall, so this is 0. You have plus Q on the outer wall of the inner shell, then this must be minus Q. All right, so Q inner of outer shell is equal to minus Q. Okay. All right, now let's move on to the next region. So next region of interest is the final region that is completely outside of the two shells. Then completely outside of the two shells, you're completely outside of any conductor, so there must be an electric field. That means the enclosed charge cannot be 0. So we already know, we have known so far, this is plus Q at the center, minus Q on the inner, plus Q on the outer, minus Q on the inner. And the overall charge, the total charge, that means the charge inner plus charge outer is equal to plus Q for the outer shell. So Q inner, Q in of out, that means Q in inner wall of outer shell plus Q out of out, that means q outer wall of outer shell, must be overall plus q. Then that means we already know what q inner of outer wall is, it's minus q. We don't know what q out of outer wall is, so that let that be whatever, and total they must be plus q. So this implies that the q outer of outer wall must be q plus little q. All right, so therefore this is a result of charge conservation and the fact that you can find the electric field using Gauss's law just by looking at the enclosed charge. Now let's go and find the potential in the easy manner. All right, so now let's start finding the potential from this region, and this region is r, the radius of the Gaussian is greater than your outermost radius, which is d. So in this region, r greater than d, what is the potential? Well, think about you bringing in a positive charge, a positive point charge, and you just placing it around this overall two shells. So we just calculated that the outer Gaussian encloses this amount of charge, right? So that means this is the net charge that the outer Gaussian encloses. That means if you were to leave a positive charge here, it would be feeling the force, and also the force per unit charge, and also basically the potential energy of this overall contribution from the two shells, and they contribute a total charge of q plus q. So let's start by writing out the general form of the potential. So potential is some whatever the charge is, divided by 4 pi epsilon naught multiplied by r, the distance from the charge. So let's write out the common factor, 1 over 4 pi epsilon 0, and then what is the charge around it? What is the charge that can influence a point charge that you can bring in, a point test charge that you can bring in? So remember, a point test charge, wherever you put it, will feel the energy from all charges around it. So if you place a point charge right here, it will just feel the potential that is caused by this overall capital Q plus little q charge. So this is the total charge that the test charge will feel, Q plus Q. And what is the distance away? So we are calling the distance of the radius of the Gaussian, that is just a small r. So quite simply, this is the potential in the region r greater than d. You didn't have to do any integral, you just had to remember this 1 over 4 pi epsilon 0 form of the potential around this sphere, right? All right, now let's move on to the next region. The next region of interest is this one. So we are walking backwards. All right, in the next region, this is now the radius of the Gaussian. The radius of the Gaussian lies in between either C or D. This is the Gaussian that we are now looking at. So this is in between this region, and this is inside the conductor. So this region is inside the conductor, and we know for a fact that the electric field is 0 inside of a conductor. So if the electric field is 0, that means inside the conductor the potential is fixed by whatever it is at the surface. So once you take your positive point charge and cross this border, the potential does not change. If the potential does not change, then the potential is fixed at the radius d. Okay, that's the first idea. Okay, so then again start off with your common expression, common factor, 1 over 4 pi epsilon 0. Then whatever you have around it, whatever that test charge that you're carrying, whatever that test charge has around it, whatever other charges the test charge has around it. So what are the other charges? So let's see. Once it's in this region, it feels the energy from the outer wall, right? It feels the energy from the outer wall, and we know the charge on the outer wall is capital Q plus little q, and that is at a distance of, just at the outer wall, that is at a distance of d. So it feels the potential, or it feels the energy due to all of the charges that are already inside the green Gaussian, right? So it feels charges, it feels the energy from outside, from the outer wall, but also from everywhere inside. It is near every other charge that is inside. So the inner wall again the outer wall of the inner shell and the inner wall of the inner shell and the charge at the center. So everything is actually exerting their effect or exerting their influence on this other charge. So we write, then you only consider the total charge that is inside this inner wall of the outer shell. So what is the total charge there? The total charge is, first you meet the charge on the inner wall of the outer shell, so minus q, and then you meet the outer charge on the inner shell, so plus q, and then you meet the inner wall inner shell minus q, and then you meet one at the center, which is again plus q. And all of these charges are enclosed by the inner wall of the outer shell, which is at a radius of c. So that is the total charge that you feel, that this test charge feels when it is in this green Gaussian region. But overall, these cancel out. So therefore, the potential is in this region is simply 1 over 4 pi epsilon naught capital Q plus little q by d. So this is in the region between the walls of the outer conductor, so inside the outer conductor, and that makes sense. The radius is not a variable anymore, the radius is fixed. That means inside everywhere that conductor, the potential doesn't change value, the potential is fixed for the one at the center. Alright, now remember one thing, remember that the potential is affected by all charges around it, not only the ones inside the Gaussian but everything around. So now let's consider this region. This is the region where we are saying this is the R is greater than B, but R is less than C. So this is the new region that we are considering. What is the potential? Well, as I said, the potential is affected by everything around, every other charge around. So if your test charge is now here, but remember you crossed the outer wall to get here. That means whatever charge is in the inner wall of the outer shell is also affecting your motion and affecting your energy. Whatever charge is also on the outer wall is also affecting. So remember, this is capital Q plus little q, and this inner wall inner shell of the outer wall is a negative q. So keep that in mind. All right, so now first let's consider the charges that are inside my Gaussian sphere. So what are the charges that are inside my Gaussian sphere? Inside my Gaussian, I have plus q at the center, minus q in the inner wall, and plus q on the outer wall. This is all at a distance of r from the center. That is the radius of the Gaussian, this radius. All right. But what is outside now? Outside, I now have also the charge due to the inner wall of the outer shell, which is minus q, and that is at a distance of c from the center. And I have charge contribution, I have potential contribution from the outer wall of the outer shell, which has charge capital Q plus little q, and that is at a separation of d, a radius of d. So then you make the simplifications, these go away. So the potential in this region is 1 over 4 pi epsilon 0 plus q over r minus q over c and plus q plus little q over d. So that is the potential here in this region that is outside of the inner shell, but in the vacuum region that is encircled by the complete outer shell. So the charge feels the energy from all charges around, inside your Gaussian and outside your Gaussian. So the potential has contribution from everything. That is quite untrue for electric field. Electric field is only affected by the charge that is inside your Gaussian. Okay, so now let's consider the last region. This is inside the inner conductor. This is the region where R is greater than A, but R is less than B. All right, and what is the potential there? That is what we want to ask. So again, start off with 1 over 4 pi epsilon 0, and then what are the charges inside your Gaussian at a radius r, and what are the charges outside of your Gaussian and outside everything. All right, so therefore your charge is now on the Gaussian, so charge is affected by the energy out of the outside wall of the outside wall of the inner shell, the inner wall of the outer shell, and also the outer wall of the outer shell. So let's write those charges down. This is minus q, this is plus q, and this is capital Q plus little q. All right, so what are the potential in this region? Well, the potential is, let's start from the inside of the Gaussian. So inside we have little q at the center and minus q at the inner wall. So therefore at a distance of r I have no contribution. These cancel out. Then let's move outside. What is the contribution from outside? Well, I have contribution from the outer wall of the inner shell, that is plus q. That is at a separation of exactly b, right? So that is r is b. And then I have contribution from this inner wall of the outer shell, that is minus q, that is at a separation of c, that is the radius. And also I have contribution from this outermost wall of the outer shell, which has charge capital Q plus little q, and that is at a separation of d. So the potential is nothing but 1 over 4 pi epsilon 0 q by b minus q by c plus capital Q plus little q by d. So all of this is constant. R is fixed at the surfaces of each of the conducting shells, because you know you're lying in the region inside of a conductor, and inside of this spherical conductor the electric field is 0. That means the potential must be constant, equipotential. All right, so therefore there is no variable r. So here you have seen that we have determined the potential everywhere in space around these two conducting shells without doing any integration.